Okay, these are going to be our notes on indeterminate forms and L'Hopital's rule. So first we want to talk about indeterminate forms. What are they and why do we care about them? So what happens is sometimes when we go to calculate a limit, sometimes we get a value like the limit is equal to 4 or the limit is equal to -6. And then other times we get limits that don't exist. They could not exist because the left-hand limit doesn't match the right-hand limit at a value, or technically even if you get a limit that approaches infinity or negative infinity, technically that doesn't exist either. But we do go ahead and say that that limit goes to infinity or negative infinity. But other times what's going to happen is when we're done calculating this limit, we're not actually going to know whether it exists or not. The limit cannot be determined while the expression is in its current form. That is not the same thing as meaning it doesn't exist. When we say that a limit is indeterminate, you don't want to think of it really as DNE. You want to think of it more as an IDK. I don't actually know whether or not this limit exists. In order to figure that out, in order to determine if the indeterminate limit exists or not, what we're going to have to do is work with it just a little bit more. So a limit is considered indeterminate if the limit results in, and I've got a little asterisk on there because you want to remember that in some of these cases, what we're talking about are your values approaching numbers, not actually being equal to numbers, not necessarily being equal to them. So we get a limit that is indeterminate if when you're done calculating this limit, you get something like 0 divided by 0. Now I have a whole set of separate notes on why 0 divided by 0 is indeterminate. It's one of the first ones we ever run into. If you would like to know why 0 divided by 0 is indeterminate, feel free to watch those. It actually gives a rather lengthy explanation. But to kind of shorthand it, the reason 0 divided by 0 is an indeterminate form is because anything multiplied by 0 gives you 0. So how are you supposed to know what 0 divided by 0 ends up being? Another example of an indeterminate form is infinity divided by infinity. Often what students will want to tell me is that infinity divided by infinity is 1 because we've trained you well. Anything divided by itself gives you 1. The problem is infinity isn't a value. Infinity is a concept. It's an infinitely large concept. So in order to say that infinity divided by infinity is 1, those infinities have to be equal to each other, and you don't have any evidence to that fact. So infinity divided by infinity is not 1, it's indeterminate. We don't know what it is. If we calculate a limit and this is what the result ends up giving us, we need to readjust how we're looking at that limit in order to determine whether the limit exists or not. Another example, 0 times infinity is an indeterminate form, because what happens is when you're going to calculate your limit, and let's say you're getting the product of two limits, and the first one has a result of 0 and the second one has a result of infinity. Well, what's going to happen is the 0 is going to attempt to make this product equal to 0, while infinity is going to attempt to make this product exceptionally large. So the question is, which one wins out in that case? Is this exceptionally large, or is it 0, or is it something in between? We don't know. Therefore, this is an indeterminate form. Infinity minus infinity is an indeterminate form, because again, what we often want to say is that infinity minus infinity must be 0. It can't be 0 unless those infinities are in fact equal to each other. And again, you don't have any evidence that they're equal to each other. So this is an indeterminate form, as is 0 raised to the 0 power, because having a base of 0 means that this limit would be trying to stay equal to 0, but having the exponent of 0 means that this result would be attempting to approach 1, because remember, anything to the 0 power gives you 1. So the base is trying to hold it at 0 and the exponent is trying to move it to 1. So which one wins? What's the result? We don't know. It's indeterminate. As is infinity to the 0. Again, infinity is trying to make this exceptionally large because it's in the base. The 0, because it's in the exponent, is attempting to make this quantity equal to 1. So we don't know what the result would be. 1 to the infinity, same thing. The 1 in the base is trying to hold the value at 1, but an infinity in an exponent is trying to grow this infinitely large. We don't know which one wins. So all of those are indeterminate forms. Let's talk about what aren't indeterminate forms. If you're calculating a limit and you get a constant divided by 0, now assuming that constant isn't 0 itself. If the constant is 0, you're over here in the 0 over 0 form. But if you get a constant divided by 0, that's not indeterminate. That's some kind of infinity going on. It depends on the constant as to whether you're going to get a positive or a negative infinity. But remember, and this is where this asterisk thing comes in, this doesn't actually equal 0. It's something approaching 0. You have a constant divided by something getting infinitely small, which overall makes your fraction get infinitely large. We understand that. We know what the result is. It's an infinity or it's a negative infinity. It's not indeterminate at that point. Neither is a constant divided by infinity. If you take some constant and you divide it by something getting infinitely large, overall, your fraction will get infinitely small. Infinity divided by a constant is not indeterminate. You're taking something infinitely large and dividing it by a finite value. It continues to get infinitely large. Things like 1 times infinity is not indeterminate. 1 times infinity, it's infinity. They're not trying to fight with each other. Neither are they fighting with each other when you have infinity times infinity. Something infinitely large times another infinitely large value is going to continue to be infinitely large. If you have 0 times 0, that's of course 0. If you have infinity plus infinity, that's absolutely going to be infinity. You don't need to know that the infinities are the same in order to have the concept that when you add them together, it continues to be infinitely large. So the moral of the story is multiplication of 2 infinities is fine, division of 2 infinities is not. Addition of 2 infinities is fine, subtraction between 2 infinities is not. So the good news is we've actually already encountered many of these indeterminate forms. I mean, think back to limits like this one. If you look at the limit as x approaches 1 on x squared minus x divided by x squared minus 1, if you try to directly substitute, which should be a natural inclination to do, what are you going to get? You're going to get 1 minus 1, which gives you a 0 in the numerator, and you're going to get 1 minus 1 in the denominator. You're going to get 0 over 0 form. That was an indeterminate form. Now for this particular limit, the technique that we used in order to change it away from something that was giving us an indeterminate form was we factored. We factored out an x in the numerator, in which case we get x minus 1. The denominator is the difference of 2 squares, so you get x plus 1 times x minus 1. We cancel out the common factor of x minus 1 so that we got the limit as x approaches 1 on x over x plus 1, at which point we could now directly substitute. We plug in 1. In the numerator we get 1. When we plug it in the denominator we get 2. So which is not an indeterminate form. That is the value of your limit. So notice you started with something that was indeterminate and ended up with something that actually did exist. Another example, if we looked at the limit as x approaches 0 of sine x over x. This is one that we first started discussing in the section where we started talking about the derivatives of trig functions. As a matter of fact, there's a very long and involved proof on why this limit ends up being equal to 1. But it's geometric in nature, and I believe it's about a 15-minute proof to get through. But notice if you start by trying to directly substitute, you'd have the sine of 0, which is 0, divided by 0. This is 0 over 0 form. It is indeterminate. After a 15-minute proof, we figured out the limit's actually equal to 1. Okay, another example. The limit as x approaches infinity on x squared minus 1 divided by 2x squared plus 1. If you try to directly substitute this, what you're going to get is infinity squared minus 1, which is infinity. And then you're going to get infinity squared times 2 plus 1, still infinity. This is the infinity over infinity form. Okay, that's indeterminate. You can't figure out what's going on with your limit based on that form. So what you have to do is you have to alter what you're looking at. And in case you don't remember, the technique for doing this is to divide the numerator and the denominator by the highest powered x you see in the denominator. So as you can see, I've divided numerator and denominator by x squared. Once I simplify, I get the limit as x approaches infinity. X squared over x squared goes to 1 minus 1 over x squared over 2 plus 1 over x squared. And remember, when we have fractions where our denominator is going to infinity and we have constants in the numerator, those are going to go to 0, both of these. So this limit ends up actually existing and being equal to 1/2. For an example like this one, the limit as x approaches infinity on x squared minus x. If you try to directly substitute, you're about to get infinity minus infinity. That's an indeterminate form. So what we did was we took the limit as x approached infinity, we factored out an x, and then we were left with x minus 1. And notice what that does is that by properties of limits, you can take the limit as x approaches infinity on x times the limit as x approaches infinity on x minus 1. Well, as x approaches infinity, the limit on x goes to infinity. This one also, the second one also goes to infinity, which changes it from an infinity minus infinity form to an infinity times infinity form. That's infinity. That's not indeterminate. So this is what I mean. We've actually run into all of these limits in previous sections. So the idea of indeterminate forms is not necessarily new. Where we start running into issues is for something like the limit as x approaches infinity on the natural log of x divided by x minus 1. If you take a look at some of the techniques we had in our toolbox to change these out of indeterminate forms, and this is an indeterminate form because as x approaches infinity, the natural log of x also approaches infinity, and as x approaches infinity, x minus 1 approaches infinity. Okay, so it's an infinity divided by infinity form. Well, doing things like factoring, which is what we did for the first example, you can't really factor natural log of x. We could go through a geometric proof, but, what if that only works for one expression involving natural log of x? What if it doesn't work for others? I mean, that was a very long proof to get one particular limit, which was the limit as x approached 0 of sine x divided by x. That seems like a lot of energy for not a lot of return. While we can divide the numerator by and denominator by x squared, it's not really going to be particularly helpful because we're still going to have a natural log of x that we can't divide the x squared into. And we don't have any factoring, which is what we did in the fourth example. So we're a little bit stuck at this point and at a little bit of a loss. So this is where a gentleman by the name of L'Hopital came up with his rule. And L'Hopital's rule says the following. Suppose f and g are differentiable and that the derivative of g with respect to x is not equal to 0 on an open interval I that contains a, except possibly at a. Okay, so your functions have to be differentiable and the derivative of g with respect to x can't be 0. Okay, now suppose that either when you take the limit as x approaches a for f of x, you get 0. And when you take the limit as x approaches a for g of x, you also get 0. Or your other possibility is that when you take the limit as x approaches a for f of x, you either get positive or negative infinity. It doesn't really matter which one. And when you take that same limit for g of x, you also get infinity. So either both limits are 0 or both limits are some kind of infinity. If you have that case, then here's something that he found as a result. Then the limit as x approaches a for the quotient of f of x divided by g of x is the same as the limit as x approaches a for the ratio of their derivatives, for the derivative of f with respect to x divided by the derivative of g with respect to x. Assuming that the limit on the right actually exists or is plus or minus infinity, because remember, technically if you get infinity it doesn't exist, but we're okay with the infinities. So instead of working with the ratio of the original functions, you can instead work with the ratio of their derivatives, and the limit should end up being the same, assuming all of these conditions are met. So let's talk about the conditions. L'Hopital's rule says that it only applies in cases where when you take a look at the limit, it results in either a 0 over 0 indeterminate form or an infinity over infinity indeterminate form. If you get anything else when you first look at that limit, L'Hopital's rule doesn't apply. This also happens to work for left-hand limits and right-hand limits, so it doesn't have to be an overall limit in order to apply L'Hopital. And please keep in mind, this is not quotient rule. You're going to do what we always asked you not to do for quotient rule. You're going to be able to take the derivative of the numerator divided by the derivative of the denominator. Only in L'Hopital's rule are you allowed to do this. So let's take a look at a limit. Let's look at the limit as x approaches 1 on the natural log of x divided by x minus 1. This is not exactly the same as the one we had on the previous slide. It's the same expression here, but in that one we were approaching infinity. This one we're approaching 1. So when we try direct substitution, in the numerator we'll get the natural log of 1, which is 0, divided by 1 minus 1, which is 0. So we are not in the infinity divided by infinity form. We're in the 0 divided by 0 form. But that's okay. That means L'Hopital applies. So this is going to be equal to, now watch the notation here. What you're going to see is an equal sign with a capital H over it. All that indicates is that I'm about to use L'Hopital. You will see that in your textbook. You will see that in the solutions manual. This is common notation when you're using L'Hopital. It's just so that when you look at the next step and you see a completely different expression, you'll know that the reason it's completely different is there's an application of L'Hopital going on. So we're going to take the derivative of the natural log of x, which is 1 over x, divided by the derivative of x minus 1, which is 1 minus 0, but we won't write that. In other words, this is the limit as x approaches 1, on 1 over x. Well, that's eligible for direct substitution, and sure enough, we're going to get 1. So L'Hopital allowed us to take something that was in an indeterminate form and change its form so that it was no longer indeterminate. We could actually determine the limit. Let's take a look at another example. We're going to find the limit as x approaches infinity of e to the x divided by 2x. And again, you need to make sure that L'Hopital applies before you go taking a bunch of derivatives. So as x approaches infinity, e to the x approaches infinity. And as x approaches infinity, 2 times infinity would give me infinity. So this is infinity divided by infinity form. It does apply. So we can go ahead and directly apply L'Hopital. We'll have the limit as x approaches infinity. The derivative of e to the x is e to the x, and the derivative of 2x is 2. So now notice that if we take that limit, as x approaches infinity, e to the x still approaches infinity. That's an infinity sign. And then 2 is a constant, so it remains. And infinity divided by 2 is still infinity. So that is now able to be determined. It went from an indeterminate form to no, the limit actually technically doesn't exist, but the limit is equal to infinity, meaning it gets infinitely large. Okay, let's look at a couple other examples. Let's find the limit as x approaches infinity on the natural log of x divided by the cube root of x. So again, we're just going to make sure we can actually use L'Hopital. As x approaches infinity, the natural log of x approaches infinity. And as x approaches infinity, the cube root of x also approaches infinity. These are both very slow growing functions, but they do grow to infinity. So we can go ahead and directly apply L'Hopital off of this. Okay. So we'll have the limit as x approaches infinity. The derivative of the natural log of x is 1 over x. And the derivative of the cube root of x, keeping in mind that that is x to the 1/3 power, its derivative is 1/3 times x to the 1/3 minus 1, which is negative 2/3. Now, let's say from here, you were tempted to try direct substitution again. That wouldn't necessarily be a bad inclination. Notice that your numerator would be 1 divided by something going to infinity, which would make it going towards 0. And then your denominator, the same thing would happen. You would end up with the negative 2/3 would put this in the denominator next to this 3, and you'd have 1 divided by something getting infinitely large, so that would go to a 0 over 0 form, which again means technically you could apply L'Hopital a second time. But watch what happens when I do that. I'm going to go ahead and do it. It's not that you can't. But when you do, the derivative of 1 over x is negative 1 over x squared. And the derivative of 1/3 x to the negative 2/3 is going to be negative 2/9. X to the negative 2/3 minus 1 is going to be negative 5/3. I don't see this expression getting nicer and easier. I see it getting harder and harder every time I do this. So while it's not incorrect to take this step, it's not particularly helpful. So let me go back to what we had after our first attempt with L'Hopital. Notice that this is a complex fraction. So it's the limit as x approaches infinity. And I'm going to go ahead and just do a quick rewrite. 1 over x, 1 over 3x to the 2/3. A lot of times if we want to simplify complex fractions, we can just multiply by their reciprocals. So we'll have 1 over x times 3x to the 2/3 divided by 1. Well, notice I'm going to get some nice cancellation going on here. So I'll have the limit as x approaches infinity. On 3, you have x to the 2/3 over x. So that's either x to the negative 1/3, that's fine, or you can do x to the 1/3 in the denominator. Either one's appropriate. But notice now, as x goes to infinity, I have a constant divided by something that's getting infinitely large. In other words, this limit will be getting infinitely small. This is going to approach 0. So when you've got a complex fraction, usually the better strategy is to simplify what you're looking at rather than taking another iteration of L'Hopital. It makes it much faster and cleaner. That's that limit. Let's look at another one. Let's look at the limit as x approaches 0 on the tangent of x minus x divided by x cubed. Okay. If we verify that L'Hopital applies, when we plug in 0, we'll get the tangent of 0 is 0 minus 0 itself, so that's 0. And then 0 cubed is, of course, 0. So this is 0 over 0 form. So we'll go ahead and directly apply L'Hopital. Okay. So we'll have the limit as x approaches 0. The derivative of tangent x is secant squared x. The derivative of x is 1. And then that's going to be divided by 3x squared. Okay, if we try direct substitution then, if we're looking for secant squared of 0, remember secant x is just 1 over cosine x, right? So the cosine of 0 is 1, so secant would be 1 over that 1, and then we're going to square it. So that would be 1 minus 1, also known as 0. And then, of course, when we plug in 0 in the denominator, yeah, that's still 0 over 0 form for us, okay? Okay, so I can try to simplify the expression rather than doing another iteration of L'Hopital, but really the only simplification you can do is to divide the 3x squared into both terms in the numerator, and let me just real quick show you what's going to happen with that. It's not actually going to work. If you do that, you'll get the limit as x approaches 0, secant squared x over 3x squared. That's an x, minus 1 over 3x squared. When you do that, again, your secant squared x, when you evaluated it 0, that's going to go to 1, divided by, your denominator is going to go to 0. I'm going to put it in quotes because technically it's not going to be equal to 0. It's just getting infinitely small. And then again, your second expression, your second term, you're going to get 1 over what is getting very close to 0 again. The problem with this is both of these go to infinity. When you have a constant divided by something getting infinitely small, they both go to infinity. So what happens is you get that infinity minus infinity form. So we don't want to go in that direction. So we are actually going to go ahead and do a second iteration of L'Hopital for this one. So if we apply L'Hopital again, what we're going to get is the limit as x approaches 0, the derivative of secant squared x. Now that's chain rule. We got to drop the 2 down first. Don't touch the inside functions. That's 2 secant x to the new power of 1 times the derivative of secant x. Now the derivative of secant x is secant x times tangent x. So I'm going to get another secant x, so that's why this is going to change to a squared, and then times tangent x, minus the derivative of 1, which is 0, divided by 3x, the derivative of 3x squared, which is going to give me 6x. Okay, so now when we try to plug in 0, which is a good instinct to have, we want to see if this fixed our indeterminate form. The secant squared of 0 is, again, 1, times 2 is 2, but the tangent of 0, that's 0. So that zeroes out my numerator. And then, yeah, I've got another 0 in my denominator. So this is, again, a 0 over 0 form. Now, that means I am technically eligible for L'Hopital again, but I'm really starting to get hesitant to do that because if you notice in my numerator, I've got 2 secant squared x tangent x, which means I'm going to have to use a product rule to take the derivative with an embedded chain rule. And while it's not incorrect, it actually would end up working out. I really want to try and do a little bit of working smart, not hard, if I can possibly get away with it. So what I want to notice is this expression has a lot of pieces to it. These are all factors. Which factors are causing this 0 over 0 form? And the answer is it's the tangent x and the 6x. The 2 and the secant squared x, those are fine. So what I'm actually going to do is make use of the properties of limits. I'm going to split this up into 2 limits. One's going to contain the pieces, the factors that aren't giving me any trouble for my indeterminate form, and the other one is going to contain the factors that are causing my indeterminate form, like this. Okay. The reason I want to do that is because this is nice. The secant squared of 0 is 1 times 2. Yeah, that one's 2. Got it. Done. Then I only have to apply L'Hopital on the second limit. So when I apply L'Hopital, what I'm going to get, I'm going to leave my 2 out here, is I'm going to get the limit as x approaches 0. The derivative of tangent x is secant squared x, and then the derivative of 6x is 6. So notice that by removing the factors that had nothing to do with the indeterminate form first, what that did was make it so that when I had to use L'Hopital for a third time in this example, it was not difficult to take. The derivative was much simpler once I split those factors off. So now we can go ahead and directly substitute again. I've got the 2 from the constant out front. The direct substitution of 0 into secant squared x leaves me with a 1, and then 6 is just a constant. That's 6. So in other words, this limit becomes 1/3. So the indeterminate form eventually became a limit that could be determined, and turns out it's equal to 1/3. Let's take a look at another one. Let's look at the limit as x approaches pi from the left on sine x divided by 1 minus cosine x. So remember, L'Hopital does in fact apply to left-hand limits and right-hand limits. Okay. However, what you don't want to do is apply L'Hopital in this particular limit, because if you check, if you directly substitute pi into this expression, you're going to get the sine of pi, which is going to be 0, divided by 1 minus, when you plug in pi to the cosine function, the cosine of pi is -1. So what you're going to get is 0 divided by 2. That's 0. You don't need L'Hopital for this one. So the reason I'm putting this in here is because I don't want you to just default to L'Hopital every time you see a limit. Some of them are much simpler. You don't need L'Hopital to do this one. It's just a direct substitution. So the moral of the story is always check that L'Hopital actually applies before you start taking derivatives for these limits. Okay, so those are my examples for indeterminate quotients. Now we wanted to discuss indeterminate products. We've already mentioned them. If you take the limit on f of x as x approaches a and you get 0, and then you take the limit as x approaches that same a on g of x and you get infinity, then when you take the limit of the product of those two functions, that's when you're going to start to get that 0 times infinity indeterminate product. Okay, so we mentioned this in the first slide that had the list of indeterminate forms on there. So it's called an indeterminate product because you're multiplying them, whereas something like 0 divided by 0 or infinity divided by infinity, these are called indeterminate quotients. So technically, when you see 0 times infinity, L'Hopital doesn't apply. L'Hopital only applies to indeterminate quotients. Or does it? Okay. Turns out, if you're willing to do a little rewriting before you apply L'Hopital, you're going to be able to use it in cases like this. If you can rewrite your f of x times g of x as either leave f of x where it is, and you need to move g of x down to a denominator, but you can't just do that because you feel like it. It's got to remain equivalent to f of x times g of x. So the way that you can do that is that you put 1 over g of x into the denominator. These are equivalent to each other. Or you can leave g of x in a numerator and put 1 over f of x in the denominator. Which one you choose is going to depend on what you're looking at. If you do that, why would this help you when you go to talk about whether or not you can apply L'Hopital? Okay. Well, let's use the limits that are up here. Let's say, yes, the limit as x approaches a on f of x is 0, and the limit as x approaches a on g of x is infinity. Then when you rewrite this as f of x over 1 over g of x, the limit as x approaches a on f of x is going to stay at 0. That's not changing. But what's going to happen when you take the limit as x approaches a in your denominator? You're going to get 1 over something that is approaching infinity. But what does 1 over infinity approach? It gets infinitely small. That will put you into that 0 over 0 form. Okay, so that's why the rewrite is helpful. If you did the g of x instead, the limit as x approaches a on g of x would stay the same. You'd have an infinity up here. In your denominator, however, what you'd get is 1 divided by something getting very close to 0, getting infinitely small. Okay, so a constant divided by something getting infinitely small gets infinitely large. So there's your infinity divided by infinity form. So when you end up with this 0 times infinity, as long as you put a 1 over one of the functions in the denominator, it should automatically put you in a form to which L'Hopital will apply. Let's look at an example. If we want to find the limit as x approaches 0 from the right on x times the natural log of x. Again, approaching 0 from the right does not change whether or not we can use L'Hopital, but we're going to verify our form first. So the limit as x approaches 0 for x is 0. And then the limit as x approaches 0 from the right for the natural log of x, that goes down to negative infinity. The fact that this is a negative infinity instead of a positive infinity does not affect whether or not I can apply L'Hopital. The sign is not as important as the fact that this is a 0 times infinity. It is my indeterminate form. Okay, we don't care if it's negative. So what I want to do is put one of those into a denominator with a 1 above it. So I'm going to tell you right now, we're going to leave the natural log of x here, and we're going to put 1 over x in the denominator. I will show you what happens if you choose the other one once I'm done doing this problem. So now notice that as x approaches 0 from the right, the natural log of x still approaches a negative infinity, but now in the denominator, 1 over x also approaches infinity. Okay, so that's an infinity over infinity form. Again, the sign doesn't matter, but it's still an infinity divided by infinity form. So L'Hopital does in fact apply. So when we take a look and we apply L'Hopital, we'll have the limit as x approaches 0 from the right. The derivative of the natural log of x is 1 over x, and the derivative of 1 over x is negative 1 over x squared. And there is that complex fraction that we looked at in one of our previous examples. We want to go ahead and simplify. So we'll have negative 1 over x times x squared over 1, which gives me the limit as x approaches 0 from the right on negative x. Once you cancel the x into the x squared, so when you directly substitute 0 in, you're going to get 0. And that's this limit. So changing it by pushing from an x in a numerator to a 1 over x in a denominator, you adjusted the forms that L'Hopital applies, and then you're able to find the limit using L'Hopital. Now, let's say for argument's sake, I had tried to put the natural log of x down instead. I would have had the limit as x approaches 0 from the right. I would have left the x right where it is, and then I would have 1 over the natural log of x down here. Well, remember what that is. That is x over, that's the natural log of x raised to the -1. And that -1, that's not attached to this x. That is not something that you can drop as a coefficient using properties of logs. In order to do that, it would have had to have been the natural log of x to the -1, where the -1 only applies to the x. Okay, and that's not what we have. So when you go to take the derivative for this, what you're going to end up with is a 1 in your numerator, and then down here you're going to get a -1 times the natural log of x to the -2 times the derivative of the natural log of x, because we're going to have to use chain rule, times 1 over x. And now it's just getting really messy because you're going to have to pop the x up to this numerator. It's not that it's incorrect, it's just not necessarily helpful. And by putting down the x as 1 over x instead, it makes this a nice, quick, simple, easy process. And I'll give you a hint. You never want to put the natural log in the denominator because these derivatives are just particularly challenging to work with. They're not wrong, they're just challenging. Okay, so that's how we deal with indeterminate products. We'll also be looking at indeterminate differences. Again, with these, it's going to be when you take your limit as x approaches a on f of x, you get infinity. And when you take the limit as x approaches a on g of x, you also get infinity, so that when you look at the limit as x approaches a on their difference, you're going to get an infinity minus infinity. Again, this is one we mentioned earlier on the previous slide, that when you get infinity minus infinity, it's not 0. In order to be 0, they'd have to be the same amount of infinity. That's not something that you can assume. So again, L'Hopital does not apply to these. Now, we're going to follow the same kind of principle we just did for the indeterminate products, though. You want to try and rewrite this expression until either L'Hopital does apply to it, or you're just able to find the limit by some other means that we have previously talked about. Okay? The difference between trying to rewrite these for indeterminate differences versus the products. The products, it was very clear. We had a very straightforward strategy, right? It was rewrite f of x times g of x and put one of them in a denominator using a 1 over. It's a very clear, straightforward, here's your process. With the differences, it's really going to depend on what you're looking at. So here are some strategies. You can either try using a common denominator if you're looking at two rational expressions. If you see a radical in your limit, it is often common to try and multiply by a conjugate. That's not new. We've seen that before. If you're looking at trigonometry, you can either try writing everything in terms of sines and cosines and simplifying, or use some of our trig identities. Or if they happen to have something in common, you can try removing a GCF. We actually already attempted that one on, let's see, on one of the previous slides we looked at this, x squared minus x. That's the technique that we used for this one, right? We factored out the x first. They had a GCF, and that's how we turned it into an infinity times infinity. So when you apply one of these strategies, you may or may not need L'Hopital once you've done that. In this case, I certainly did not. So when I will look at an example, like find the limit as x approaches pi over 2 from the left on the difference between secant x and tangent x. As you approach pi over 2 from the left on secant x, remember that that one has a vertical asymptote at pi over 2. Pi over 2 has a vertical asymptote, secant x has a vertical asymptote at pi over 2, and that the graph does this on the left-hand side. It looks kind of like a parabola in there. So as x approaches pi over 2 from the left, secant x goes to infinity. And similarly, tangent x also has a vertical asymptote at pi over 2. Only that one, instead of looking like the parabola, it looks more like a cubic, but it also goes to infinity as x approaches pi over 2 from the left. So there's your infinity minus infinity form. Okay. While I have lots of identities that involve secant squared x and tangent squared x, not quite as many for the just plain secant x and tangent x. So I'm first actually going to try and rewrite this in terms of sines and cosines, and let's see if I can clean that up a little bit. So we're going to let x approach pi over 2 from the left. Secant x is 1 over cosine x, and tangent x is sine x over cosine x. And notice they just became two fractions, and they happen to have a common denominator, in which case I can go ahead and combine them. If they didn't have a common denominator already, I could go ahead and attempt to get one. But so I'd have 1 minus sine x in my numerator and cosine x in my denominator. So notice now what I have. If we directly substitute pi over 2 into sine x, what I get is the sine of pi over 2 is 1, so I get 0. And then the cosine at pi over 2 is also 0. Oh, so that changed it to a 0 over 0 form. And as soon as I do that, now I know L'Hopital applies. So I can go ahead and take the limit as x approaches pi over 2 from the left-hand side. And I'm going to take the derivative of the numerator and the derivative of the denominator. The derivative of 1 is 0. The derivative of sine x is cosine x, so I'm going to leave the negative as is. So I'm going to have a negative cosine x divided by the derivative of cosine x is negative sine x. So those negatives definitely cancel out, but in addition, when we directly substitute pi over 2 in, the cosine at pi over 2 is still 0, but the sine at pi over 2 is 1. Now I'm out of all those indeterminate forms, and I'm able to determine that the limit is in fact equal to 0. Okay, so that's that one. Let's find the limit as x approaches infinity of the square root of x plus 1 minus the square root of x. When we look at this, we see that as x approaches infinity, the square root of x plus 1 will approach infinity, as will the square root of x. So this is my indeterminate difference, my infinity minus infinity form. What I'm seeing are radicals, so I'm thinking conjugate. So I'm going to multiply by the conjugate. So that's the square root of x plus 1 plus the square root of x. But of course I can't just multiply by that because I feel like you have to follow the rules of algebra, which means I need to multiply the denominator by that as well. There's your well-chosen 1. Okay, so when I do that in the numerator, I'm going to have the limit as x approaches infinity. In the numerator, I'm going to have x plus 1. The outside and inside products will cancel each other as one is positive and one is negative. And when I multiply the lasts together, it will give me a minus x over the square root of x plus 1 plus the square root of x. And definitely those x's go away because one's positive and one's negative. So we get 1 over the square root of x plus 1 plus the square root of x. Now notice something. That means my numerator is now a constant, a non-zero constant, which means I don't even need L'Hopital to do this. That's nice and set. If you take a look, what's going on in your denominator is you now have infinity plus infinity as you take your limit. And remember, infinity plus infinity is not indeterminate. It's infinity. So what you have is 1 divided by something getting infinitely large, in which case the fraction overall gets infinitely small. This limit is equal to 0. And I, again, didn't necessarily need L'Hopital to figure it out. But there are times that you will need L'Hopital once you simplify your expressions, as in the example up here. So we just like to have that in our back pocket in case we need it. So lastly, what we want to talk about are those indeterminate powers. And again, we talked about the 3 kinds, 0 raised to the 0 power, infinity raised to the 0 power, and 1 raised to the 0 power. These are all indeterminate forms, but because they have bases and exponents, we refer to them as indeterminate powers. So what I want you to pay special attention to is what kind of expression you are looking at to end up with an indeterminate power. Take a look at this limit. It's the limit as x approaches a on f of x raised to a function g of x. This is a function in both the base and in the exponent. In other words, you're going to expect to see variables in both the base and the exponent. That's when your indeterminate powers start to arise. So while we don't see this as often as we see a lot of these other indeterminate forms, they do arise on us on occasion. So we follow the same strategy. We rewrite our expressions so that L'Hopital can apply. And the first step in doing that is to make sure that you don't have variables in both the base and the exponent, because as long as that holds, you're not going to be able to use L'Hopital. So we've run into this a little bit before when we were talking about derivatives. Usually the most straightforward way to accomplish this, if you want to make sure that you don't have variables in both your base and your exponent, when we want to get things out of exponents, that's when we tend to want to introduce a logarithm. But you can't just, go back up to this limit and say, hey, I'm going to put a log here. You can't do that. It would make it not equivalent to the limit you're attempting to find. So what we need to do is introduce a log without altering our expression, and that's where the cancellation equation comes in. Notice that in general, if you have something and you want to just magically kind of, hey, I want to put a natural log in front of this because it'll make my life easier, what you do is you take the natural log of that, but then you put the whole thing in an exponent with a base the same as the log. And we're going to stick with base e because that tends to be the easiest for us to work in. So that's the cancellation equation that we're going to make use of. Let's take a look at what that looks like in an actual example. So let's find the limit as x approaches 0 from the right on x raised to the x power. So this is about as straightforward as I can get for you. These aren't real complicated functions. It's just a variable in the base and a variable in the exponent. Notice when we try to do direct substitution for this, that would be that 0 raised to the 0 form. Okay, it's indeterminate. So what we want to use is the fact that x raised to the x is the same thing as, we want to put a natural log on x raised to the x, because what that's going to eventually allow me to do is to drop my x down as a coefficient. But these two things aren't equal if I write it like this. In order to make them equal, I need to put an e in the base here. Okay? So once we do that, we are in fact allowed to drop the x as a coefficient. Now remember, that means it drops as a coefficient in front of the log. It's still in the exponent of e. Okay? So this is what we're going to take the limit of. We're going to take the limit as x approaches 0 from the right on e raised to the x ln x, since it's the same as x raised to the x power. This is going to get a little complicated if I leave it written like this. So we're actually going to start here. Start with your exponent and see what that's approaching. So I'm going to look at the limit as x approaches 0 from the right on x times the natural log of x. We'll come back for the e in just a little bit. Now that one should look familiar. When we directly substitute the 0 in, this is going to be a 0. The limit as x approaches 0 from the right on x gives me 0. And as x approaches 0 from the right on the natural log of x, that goes to negative infinity. There's that 0 times infinity form. Technically it's negative infinity, but remember we don't care about the sign. We actually already did this example on one of our previous slides. So that's an indeterminate product. So the strategy is to take one of those two and put 1 over it in the denominator. And remember, it's never the log. So we've got natural log of x over 1 over x. That's now going to be an infinity divided by infinity form, and which means it's now eligible for L'Hopital. Here we go. So we'll have the limit as x approaches 0 from the right. It's an arrow. The derivative of natural log of x is 1 over x over negative 1 over x squared. We did all this work, so I'm kind of going a little bit fast. When we cancel those, we get negative x, so that limit ends up being 0. Okay? So what we've done is back to our original limit, which was the limit as x approaches 0 from the right on e to the x ln x. What we've done is figured out as x approaches 0 from the right, what's happening to the exponent. So watch this change in notation. This is actually kind of common. So we figured out what's going on in the exponent without taking e into consideration yet. So we're going to leave the e, and we're going to do what's called replacing that exponent with a dummy variable. Any dummy variable will do. Usually the default is t, okay, but you can use anything. And what we're going to say is, hey, we figured out that t, the exponent, is actually approaching 0. That's what we did in this big long work right here. Our exponent's going to approach 0. So we're going to replace the exponent with t and let t approach 0. Well, that's a direct substitution. In other words, this limit is going to go to 1. So it's kind of some weird notation using the dummy variable in there, but that's usually what you're going to see when you look in your calculus book or when you look in your solutions manuals. That way we can just kind of focus on the exponent without having to worry about the e, and then we come back for it later. So let's take a look at a slightly more complicated example. Let's find the limit as x approaches 0 from the right on 1 plus sine of 4x raised to the cotangent x. So again, what's going to tip me off is I'm seeing an x down here in a base, and I'm seeing x up in the exponent. If we try direct substitution, the 4 times the 0 will give me 0. Sine of 0 becomes 0, and 1 plus 0 gives me 1. And then in the exponent, we've got cotangent x, which remember is cosine x over sine x, which means it has a vertical asymptote at 0, which means it's going to some kind of infinity. Okay, again, positive or negative infinity doesn't change how we'll approach this limit, so it doesn't matter for the purposes of the limit, but this is the 1 to the infinity form. So that's an indeterminate power. So what we need to do is rewrite what we're going to take the limit of. What we really want it to have in it now is a natural log of 1 plus the sine of 4x raised to the cotangent x. Okay, the reason we want that is that it will allow us to drop that cotangent x down out front of our natural log. But we can't just write it like this. It's not equivalent. So you got to use the e. Okay. In other words, now I can drop the cotangent x out front of the log. They are still, however, up in the exponent. Oops, sine of 4x. That's a sine. Okay, so I need to pretty much just, for now, let's just focus on that exponent. Otherwise, this is going to be too many things to try and keep track of all at the same time. So we're going to look at the limit as x approaches 0 from the right on the cotangent of x times the natural log of 1 plus sine of 4x, which looks absolutely terrible. I mean, that looks like a limit that has a lot of moving pieces to it, and it absolutely does. So let's just go with what we know. We always try direct substitution first. The cotangent of 0, because it's cosine x over sine x, remember that sine x has a vertical asymptote at 0. So cotangent x as you approach 0 goes to some kind of infinity. When we directly substitute into the natural log function, the natural log factor, when we plug in 0 to the sine function, we're going to get sine of 0, which is 0, which means we're looking at the natural log of 1, and the natural log of 1 is 0. So this is infinity times 0 form, which is a good thing for us. That means we have an indeterminate product. We're going to be able to rewrite this so that we can apply L'Hopital. One of these needs to go down to a denominator with a 1 over it. And like I said, it's pretty much never the natural log. So we're going to have the limit as x approaches 0 from the right. I'm going to leave that natural log in the numerator, 1 plus sine of 4x. Now, in the denominator, you can absolutely write 1 over cotangent x. That's not wrong. But remember, eventually, I'm going to have to take the derivative of this thing. So what is 1 over cotangent x in terms of other trig functions? Well, that's tan x, and that is way easier to take the derivative of. This changes me to a 0 over 0 form, which means I am now allowed to apply L'Hopital. So when I look at this, I'm going to have the limit as x approaches 0 from the right. the derivative of the natural log of 1 plus sine 4x. Okay, it's going to be 1 over whatever's inside your natural log function. So that's 1 plus sine 4x times the derivative of that inside function. So the derivative of 1 is 0. The derivative of the sine of 4x is the cosine of 4x times the derivative of 4x, which is 4. So that's actually a double chain rule. Okay, so that's the derivative of the numerator. I then need to divide that by the derivative of tangent x, which is secant squared x. Okay, and I'm going to be real honest with you, that's not pretty. Okay, that doesn't look like anything I actually want to simplify. So what I'm going to try to do before I decide to put in the effort of simplification, I'm going to try direct substitution and see if L'Hopital helped me out. So what I'm going to get is 4 times the cosine of 0 ends up being 1, divided by 1 plus the sine at 0 ends up being 0, divided by, remember secant is just 1 over cosine, so the cosine of 0 is 1, 1 over 1 is 1, and 1 squared is still 1. And notice what that's going to do. That's going to give me a 4 over 1 up here, over 1, it's 4. So sometimes you'll still have to simplify these, but by all means, if you can avoid extra algebra and extra simplification, please feel free to do so. So this limit of the exponent ended up giving me 4. So when I looked at the limit as x approached 0 from the right on e to the cotangent x ln of 1 plus sine of 4x, what I determined is that as x approaches 0, the exponent approaches 4. So what I'm going to do is I'm going to replace that exponent with something, so I don't have to rewrite it again, and say, hey, I looked at that something doing all of this work, and that something approached 4. Well, now that I have it as simple as this, it's a direct substitution. So this limit, the original limit, is now equal to e to the 4th power. And that is indeterminate powers.